Hello, my name is Heather Kulik. I'm a professor of chemical engineering and chemistry at MIT, where my group runs a research program in computational chemistry and machine learning for the discovery of new materials. And today I'm going to tell you a little bit about my group's research. So, a lot of what we spend our time thinking about is the exploration of what I like to call transition metal chemical space. And that's the space of all possible ways transition metal complexes can be formed by taking metal centers and surrounding them with different ligand fields. And if we zoom in on this space, we can think about how we would go about exploring it using computational methods. Now, the right transition metal complex for a particular application might be in any one of these different islands and different spaces. And in particular, we might want to be able to develop a computational framework for knowing which part of a transition metal complex um, really gives rise to its optimal properties, say in energy storage or in catalysis. And so early on, we were interested in answering the question, what does it really take to accelerate the discovery of new transition metal complex structures with optimal properties using computational chemistry? Do we really need to know most about the electronic structure of the metal center? Do we care about the atoms directly coordinating to the metal? Or maybe the properties of a transition metal complex are dictated much more by what's going on overall in the structure of the material. And the reason, again, that we care about this is because a lot of the most interesting and atom economical catalysts that can carry out difficult chemical transformations are transition metal complexes or metal organic frameworks or so-called single atom catalysts that have this motif of this metal centered with organic bits around. Then there are also applications in energy storage as well as in the separations of gases or liquids, where having these metal centers can really give rise to good properties in the materials. But the same things that make these materials interesting also make them challenging to study because the metal center has difficult electronic structure, meaning that complex quantum mechanical models are needed to accurately predict their properties normally. But where does data-driven methods and where do machine learning come into this? So it turns out that machine learning, even though people talk about it more and more these days, it's not necessarily new in chemistry. So for decades, going back to the early days of chemistry, people have inferred and developed ways of detecting patterns in data sets and using those insights to build predictive models. Early examples include the Tolman cone angle from 1970, where the angle formed by phosphine ligands could be used to predict how strongly phosphine ligands bind to catalysts as well as how reactive they are. In 1976, Verloop developed something called sterimol parameters, and these have been demonstrated over the past 10 or 20 years by Matt Sigmund for catalysis. In particular, you can predict the experimental yield of a reaction if you know this particular parameter that describes the shape of a catalyst. There are other things like buried volume, so how buried is the metal, and that can tell you a lot about how strongly different species will bind. You can basically think of this buried volume as a generalization of the Tolman cone angle. Then there were other things like the COMFA descriptors that describe the basically the electrostatics around a catalyst, and these have been successfully applied to predict experimental measures of catalysis. Then there are more quantum mechanical models. Jens Norsko developed something known as the D-band center model that could tell you for a bulk catalyst how reactive would it be based on where its d electrons are. And then there's all sorts of multivariate combinations of these types of descriptors developed by a large number of chemists in the past 20 or 30 years. What was different about this era of data-driven chemistry versus what we think about today is that analysis was often limited to simple linear models, limited to a small number of molecules or catalysts, or specific data set types. So where does machine learning as we know it today come in? Well, machine learning itself is also not necessarily that new. So the first artificial neural networks were developed in the 1940s, multi-layer perceptrons, and the backpropagation method that allowed for training of machine learning models was really developed in the 50s into the 70s and 80s. And alongside those developments in computer science, the first developments in in chemistry also came about. So the first classifier that could detect mass spectra or do pattern recognition on chemical data. This was starting to be done in the 1970s as well. Then in the 1980s came about the first neocognitron, which is the predecessor of the convolutional neural network. And in turn, in the 1980s, there were the first models to predict protein secondary structure, something that won the Nobel Prize just this year, had actually been had its roots back in machine learning in the 1980s. And then the 1990s, true convolutional neural networks were starting to be developed, and you start to see more branching out in how people are applying machine learning in chemistry, including predicting reaction outcomes, predicting outcomes for heterogeneous catalysis, solving the Schrödinger equation, and developing neural networks for quantitative structure activity, reactivity. So all of the applications we think about modern machine learning for today actually have their roots back into the 70s, 80s, and 90s. And what's changed really in the past 20 years is GPU acceleration of ML model training, the availability of software, open source ML toolkits for training machine learning models. And this has really led to the widespread use of machine learning in chemistry. But just to emphasize that people thought that this was not the first time that people thought machine learning was taking hold in chemistry. So here is a poster summarizing the 203rd ACS, American Chemical Society National Meeting that took place in San Francisco in 1992. There was a session on neural networks in that very ACS meeting. And you can see from the titles here, neural networks as a tool for interpretation of multispectral data, neural networks for simulating carbon-13 NMR spectra. These types of talks are talks that we would think of as being modern 30 years on. And so it's just important to remember there were lots of lessons learned going back quite some time of machine learning and chemistry, and machine learning and chemistry have often been quite close in terms of their development. Another thing that I find entertaining, if you go back into this literature, this early surge in the 1990s, is this actual graph here where people were pointing out the exponential growth in publications related to neural nets. And they were pointing out that, wow, in 1991, they had a lot. They had 110 papers as opposed to only 3 in 1998. Of course, we probably publish about 110 papers a week at minimum on machine learning and chemistry now, especially neural nets. But this is just a fun piece from history. So in particular, as I mentioned, my group is really interested in transition metal chemical space, which has unique challenges as opposed to other areas where machine learning is applied. We have an extreme diversity and very large size of ligands that can coordinate a metal center. And then when we coordinate metal centers in different ways, this results in a different possibility of the spin states of the metal center, especially if it's a mid-row transition metal. And the mid-row transition metals themselves can sample a very large number of oxidation states. So what my group has developed over the years is a toolkit for automating the structure generation of transition metal complexes. It's called MultSimplify. We also developed graph-based representations that were tailored for transition metal chemistry by really allowing for adaptive focus of what's going on at the metal center or what's going on further away, but not requiring precise 3D geometry information. This led us down the path of training the first machine learning models, specifically neural nets, to predict things like the quantum mechanical spin state of a transition metal complex. We also developed what's called uncertainty quantification metrics, specifically something known as the latent space distance, that basically told us how uncertain is our machine learning model when we train it. And this is something that's really important. We can train a model and then apply it widely, but we may not trust it in certain spaces. And so we can either do something called model exploitation, so use the model only where it's most confident, or we can do something called model exploration, where we look for the unconfident regions where the model thinks there are promising compounds, but it's not sure. And then we go back and we do what's called active learning. We generate new data with DFT and then repeat the process of model training again. And ultimately, our goal is to come up with new design principles, new ways to think about that atom by atom design of transition metal complexes and new lead materials. So I'm going to get into a couple of more details and give you a couple examples of how we've done this in transition metal chemistry. And so specifically about the representations I mentioned, we exploit metal local representations for open shell transition metal chemistry. And specifically, we developed something called revised autocorrelation functions, which are called that because they're based on Moreau-Brodo autocorrelation functions, and they're products and differences on the molecular graph of heuristic properties. And these heuristic properties are nuclear charge, electronegativity, which we call our more electronic descriptors, or covalent radius, topology, and identity. And all of these can be just looked up in a table. So they don't cost us anything to compute them. And training machine learning models on modest data sets, we're able to achieve about 1 kilocal per mole accuracy with respect to DFT training data to predict the quantum mechanical spin state of a transition metal complex. This does a lot better than whole molecule representations such as the Coulomb matrix because it allows for adaptive focus towards the metal center where that is most important. And here I'm showing you the full rack feature vector as well as after feature selection where we only keep the most informative features. And looking at the most informative features through something called recursive feature addition, we can see which features are most important for predicting a property. And here I'm showing the pie chart of the most important features to predict spin, right next to a pie chart showing the most important features to predict redox potential. And what you notice is that you have a lot more blue, red, and green in the left pie chart. And what that means is that the spin of a transition metal complex is much more dictated by what's going on at the metal center and the first two bonds away from the metal center, whereas the redox potential is a much more overall global property of the transition metal complex. So analyzing these pie charts can tell us a lot about how to do molecular design. The other thing we can do is this model exploration I was mentioning. And here I'm going to show you the first example of where we applied this model exploration in materials discovery. So redox flow battery, redox couple design is one way to address some of our energy challenges. And some of the key things we have to think about when we design redox coupled for redox flow batteries is we need them to be stable and resistant to crossover. We need them to be in good concentration in the polar non-aqueous electrolytes, and we need them to have a high redox potential. So we address the stability and resistance to crossover by designing a novel pool of candidates that will be big and bulky. And we take 30 common heterocycles, fuse them together to form 779 ligands, add functional groups and metals, and this gives us a space of 2.8 million transition metal complexes. To exhaustively screen all of these big complexes, most of which have 100 to 200 atoms, with DFT would take us decades, so it's impossible to do this without machine learning. And then for addressing solubility and redox potential simultaneously, we're going to do something called efficient global optimization with the 2D expected improvement criterion. I'll show it as a cartoon here on the first slide, and then I'll show you the real world example of the data on the next slide. So we have our two objectives. Those are log P for solubility and the redox potential. And we're going to go out and we're going to collect DFT data, maybe take a couple weeks doing this. And we're going to train a neural net and we're going to ask the neural net, what do you think of these 2.8 million compounds? And what we're looking for is points that are likely to push past the Pareto front of both high redox potential and good solubility. And so we're going to look at the points that go back past this Pareto front that are both promising and uncertain. So they score highly with the 2D expected improvement criterion. We're going to take the best candidates by clustering, and we're going to go back to DFT. And we will have been right about some of those points and wrong about other points. We're going to recalculate those points, retrain the model, and do the whole thing over again. So this is what it looks like in practice. So we have about 2 weeks with DFT. And after about 2 weeks with DFT running 64 GPUs full throttle on my group cluster, this is what we see. Not very impressive. It's only about 100 points. And then we go to the neural net. And after about 3 minutes, this is what we see after having trained the model. And here's the Pareto front on both graphs. And we can see that the expected improvement scores lit up very brightly going past this Pareto front. So we select a cluster of points from the neural net, and then we go and we carry out DFT calculations on them. And you can see this time we didn't push the Pareto front too far. The neural net wasn't very accurate in its estimation of where these points would end up. But we can retrain the model. That's what we've just done. And after another few minutes with the neural net, we now pick out new points. for carrying out more DFT calculations. And this time we do a lot better. So now we've spent about 4 weeks with DFT and about 9 minutes with the neural net. And the other thing you'll notice is that the neural net is getting increasingly pessimistic that any new points are going to push further past this Pareto frontier. So we'll spend another week with DFT, and then another few minutes with the neural net, and we're at generation 4 now. And after actually about 5 generations, we're going to stop with DFT. And you can see that there are very few points left expected to move past the Pareto front with the neural net. And in fact, the final Pareto frontier we have consists of only points from generations 3, 4, and 5 of the model. And we can look at what design principles we can extract from this Pareto front. The main thing we notice is that it's good to have these rings with sulfur in them. That helps a lot for having good redox potential. If we want to have really bulky ligands, then that helps a lot with the solubility, but at the cost of worsening the redox potential. And this is consistent with that pie chart I showed you for redox potential earlier in my talk. And in particular, manganese high-spin compounds with oxygen coordinating atoms, sulfur in the ring, and then small polar groups, those help to increase solubility without worsening redox potential. And if we compare how quickly we found these design principles to just randomly searching the space, we find that we have at least 500-fold acceleration. And the first time I heard 500, I was like, that's not very fast at all. Anyone could do something 500 times faster. But it took us 6 weeks running this high throughput on 64 GPUs. And so you can quickly do some math and take 6 and multiply by 500 and realize that this is the answer difference between having an answer in a month versus not having an answer for decades. So really now the challenge is not getting this working, but figuring out important design challenges to address with this type of workflow. And now I'd like to finish by telling you one more story where we've really addressed the question of how do you look at addressing the synthesizability gap. So everything I just showed you were hypothetical compounds, but there are also cases where what we want to do is we want to make a computational prediction and then see that realized in the lab. So that's what I'm going to tell you about now. And this particular application is a field known as polymer mechanochemistry. And what's interesting about mechanophores is they're molecules. Here's an example of a ferrocene mechanophore. Most mechanophores are organic molecules, but ferrocene was one of the first studied transition metal mechanophores. And ferrocene, when the two cyclopentadienyl rings aren't linked, it breaks at a higher force than when they're conformationally locked together. And what's interesting about mechanophores is if you put many weak mechanophores into a polymer network, it actually strengthens the overall macroscopic properties of a polymer. So we were interested to know if we could design a mechanophore, ferrocene mechanophore that behaves like the conformationally locked one, but all through non-covalent interactions that would make them compatible with polymer networks. And the reason that we're interested in this is because if you look into the Cambridge Structural Database, which is a repository of experimental structures, there's actually around 5,000 well-behaving ferrocene structures that are all unique in the CSD. So only a handful of ferrocenes have ever been studied for mechanochemistry, but there's 5,000 that people have already figured out how to make that have synthesis recipes that are well characterized and so on. And so that's exactly what we targeted. So after attaching polymers to these 5,000 structures, we end up with about 12,000 unique candidate ferrocene polymer combinations. And we use a simulation technique called constrained geometry simulated external force, or COGEF, to estimate the force at which these different ferrocenes would break apart. And we did it for about 3% of the overall 12,000 combinations we could have chosen. And what we find here is that indeed, if you have the covalent linkage, then you can break apart these ferrocenes at lower forces. But there is a long tail for these ones that aren't covalently linked that go down to relatively low forces. So we trained a classifier model on racks to predict the difference between low force and high force, which we distinguish at 3,500 piconewtons. And we could do this to really pretty good accuracy. And then we use that model to predict where else in the space we could find low force mechanophores. So after just a single generation, what we were able to do was greatly enrich the number of mechanophores that were predicted to be below this 3,500 piconewton threshold. And we stopped after one generation because we found that there weren't too many predicted to still exist that we had not yet characterized. So then we suggested a couple of these candidates for synthesis. And so the first one we identified for synthesis had this bulky group around, as well as a carbonyl. Nuseg was its CSD ref code, but and that's the blue line here. And what we want is this line to cross this black bar at a lower force. The experimentalists told us, okay, just the bulky group is a lot easier for us to synthesize. That's what's shown in red here. So we said, okay, sure. And the control here is what's shown in green. And we characterized some of the electronic properties, the reasons why we predicted this to have lower force. And indeed, when they did the experimental synthesis and tear test, what they found was that you could actually stretch our material 4 times longer than a standard covalent polymer network just by having this MTMSFC in it. So the design material had over 4-fold increase in network toughness, all from like molecular scale computational predictions. And what's really cool about this is even a phenomenon you can see with your eye. So all 3 of these materials are going to tear. The controls on the left, the material we designed is on the right, and the material we designed is actually going to tear last of the 3 materials. So this is something that we can go from making predictions computationally to something, a phenomenon we can actually see with our eye. And this is the kind of thing that I think is the future for machine learning and chemistry. So I'd just like to finish by summarizing what I've told you. We as chemists have always been people looking for patterns in data. And the only thing that's changed in recent times is that we have more data and more toolkits available to us. And it's possible now to discover new lead compounds. The real challenge is figuring out what types of questions and what types of problems are suitable to target. We still suffer from challenges associated with where we can get data, how good that data is. And new tools are being developed every day. Things to think about going forward. Large language models obviously have the potential to accelerate some types of learning dramatically, but there are new questions and opportunities being introduced every day by generative AI. Autonomous experimentation is a big one, but there are certain types of experiments that are still extremely challenging for autonomous experimentation. And the key things to think about are, what do we consider to be our real deliverable? What do we do when we're being expert chemists? Which types of knowledge-based work that we do is the most valuable, as it becomes possible increasingly for machine learning models to do a lot of things we might have done by hand. And which scientific questions are just really hard to answer with AI and ML, but are easy for humans to deduce and answer. And how much do we want our work to be automated? And in what way should AI models be in the loop? So thanks for listening to my presentation. I'd just like to acknowledge the students who did the work. Much of the work I told you about today was work done by John Paul Janae, an early graduate student in my group, but I also had the chance to tell you about work by Ilya Kevlishvili, Aditya Nandi, and others. And thank you for your attention.